really what I wanted to do, since all of you kind of frustrated from first year and probably you never felt the scope of surveying. You never felt how important surveying is. Uh, I think even if you go to school, even if you do it online, probably by now you know a little bit about surveying. So really what I wanted to do in this 1 hour is to kind of expose you to what surveying is, and just give you a heads up, surveying is not only what you have seen in the first year. It is way, way beyond what you've seen the first year. And that's why my agenda for this session is very simple. I am going to tell you what surveying is in a nutshell, what surveying is, and then we'll take you into specialized types of surveying where you will see the challenge, the real challenge of surveying in some applications. Okay, let's start. So I can tell you something, surveying is just all about one word, one question. As soon as you ask the question where, then the answer is surveying. Whenever you say where, it means the answer is from the surveying. And this question where, it can expand, which means instead of saying where, and I can ask about location, I can ask about height or height difference, I can ask about areas, I can ask about angles, length, volumes, topography, like where are the flat areas and where are the steep slopes. And you can see from this slide, looks, it's very simple, very simple. Once you say where, it means we're saying we're doing surveying, okay? However, I can tell you, things will get so complicated. So surveying has so many branches. And every branch, you can look at surveying from different perspective. You can classify surveying based on so many aspects. Here we go. We can classify surveying according to the area to be mapped. So sometimes we map or able to make a map for a small area on the earth, and sometimes our area that we want to map is as big as Alberta, or maybe Canada, or maybe the entire world. Is it the same? Are we going to use the same equipment, the same procedure, the same calculation? The answer is no. We have different business, and I will talk about shortly about in more details about plane surveying and some is called geodetic surveying. We can also look at surveying from different perspective, which is what is the field of the application or the objective. Oh, really? It means when I do a tunnel survey is different from I do the deformation survey, or maybe when I build a high-rise building, or maybe when I do surveying underwater. Yes, it is completely different, where you need to change the entire procedure and sometimes use a very specialized equipment. And also, when you look at surveying, you can look at it from a different perspective, which is which equipment I'm using. Am I using total station or GNSS or photogrammetry or laser scanner, where the product is almost the same? So whether I use total station or GNSS or photogrammetry as a scanner, you end up with sets of coordinates like X, Y, Z, okay? But you will see quite different between all those techniques in terms of application, in terms of availability, in terms of the density of the point, and so on and so forth. So let's start and give you more information about each of those individual categories. Now, I think, let me ask you this question. What do you think about the actual shape of our Earth? Okay. Anybody in this class still believe that our Earth is flat? I want to know. I'm interested to meet you if you are interested, if you still think that our Earth is flat. Okay. So our Earth is not flat. However, it looks pretty much like a sphere. It's not really a perfect sphere, but pretty much like a sphere. And so how this can affect my survey? Now, let me ask you this question. If you fix 3 points on the ground, if you fix 3 points on the ground, and then you have an equipment that can measure the angles, which is total station. Okay, so for example, I have 3 points, point A and B and P, and those 3 points are on the ground. And I go ahead, I measure the angles like alpha and in my screen and the angle between line AB and AP. Now, let me ask you, when you measure those three internal angles of a triangle, what do you think? The sum of these angles should be a specific number? I need some help, please.
Yes, 180.
Thank you so much. From the geometry, if you have a plane triangle, then we know from math that the sum of the internal angles is simply 180. And we know that when we use total station to measure the angles, there is some sort of error will happen. There is a measurement error. And then this measurement error, it simply quantifies how good or how bad. For example, if I measure the three angles and the three angles, I add them together and then it's 180 degrees, 0 minute, and then 30 seconds. You know what? I know that I have made 30-second error in my measurement, if you agree. Now, you can see I used all plane trigonometry to do my calculation. However, if I just expand the area, which means A and B and P, they are not close to each other. What happens is if I simply take 3 points far apart, and I will take it to the extreme. Extreme, it means, let's say I have 3 points, alpha and beta and gamma, and alpha happens to be on the North Pole, and beta and gamma, they are happening on the equator. Probably you're familiar with the word North Pole, equator. Are you?
Yes, we
I
are.
think so.
Okay. Now, let me ask you, please look at my screen, the picture on the right. As I said, I pushed the extreme, so I pushed these 3 points very far from each other. I'm asking you right now, do you still think the internal angles of this triangle, which is not really plain triangle anymore, it is called spherical triangle. Do you think the internal angles, the sum is still 180? Yes or no?
Yes.
No.
Okay, so whoever said yes, let me show you that you were not right. Now, do you know something called the meridian? So the green side and the blue side, the green and the blue, those are half meridian. And the meridian is simply half circle that passes through the North Pole and the South Pole. Okay. Now, do you know the angle between a meridian and equator? Anybody knows what's the angle between the meridian and the equator? Okay, so I'll make your life easy. The angle between the meridian, which is in green and blue, and the equator, which is in red, the angle is 90 degrees, which means 90 plus 90. So right now, only two angles, and we are at 180 degrees. Okay, and we haven't really accounted for the angle at a point alpha, which means if you have a spherical triangle, the sum of the internal angle is not 180 anymore. However, it is 180 plus something called spherical excess, extra more than 180. You know what? I'm not gonna dip you deep into that spherical trigonometry. It is more difficult, and all I'm trying to say here is that the area that you're trying to map, it will dictate the way that you estimate and calculate. So that's why in this context, we have two kinds of surveying. One easy, very simple that you learned last year called the plane surveying, where the area is very small and we can simply approximate the surface of the earth into a flat surface. However, we know that the actual shape of the earth is almost close to a sphere. When the area is so big, then We need to take the curvature of the earth into consideration, and this will take us into different worlds. And in my class, at the very end, before we end our semester, I will give you more information about geodetic surveying. Okay, that's only for now. Now, let's take you to another domain, which is tunneling. So we are trying to build a tunnel, and we want our surveyor to help us to build the tunnel. Because I can tell you, there is no construction without surveying. I want everyone to believe this. There is no construction without surveying. Without surveying, you cannot build almost anything. Okay? You cannot. Not you can. You cannot build anything without surveying. So when you're trying to build a tunnel, and I think we have few tunnels in Calgary, okay? Anybody can give me an example of tunnels in Calgary similar to what you see on my screen? If you take the C train, you will know.
To get it to the airport from the east, there is another tunnel.
Yeah, there is a tunnel also if you take the C train going to the west, you will go through so many times. Even if you take the C train from the north to Sate, there are few tunnels, okay, under Rothschild. So tunnels is kind of complicated topic, and we can build them in two ways. First one is the easiest one. The easiest one is what you see on my screen. Simply, it's called open cut or cut and cover. So you just have to dig the ground, and once you dig the ground, you simply install your retaining wall, and then if you need to cover, make a box section, then you build the slab, and then finally you cover with soil, and it's good to go. And so you know, this kind of tunnel, it's called open cut, doesn't require anything more than what you learned in the first year, because simply it's open cut from the top. You can see the bottom. You can simply locate all the points on the tunnel as per the design, so no problem. Okay, the thing is, this technique doesn't work all the time. You know why? You know why this technique doesn't work all the time? Because simply you have to make an open cut. So let me ask you, look at this situation right now. You have a city which is already built, let's say a few hundred years ago. For example, like Cairo. Cairo is built 100 years ago, I would say more than 1,000 years ago, okay? Now the city is there and you don't have much space, and you have a problem with the transportation. You want to build an LRT. Now let me ask you, how can you do that? Should you demolish all the building and then make the open cut, build the tunnel, and then cover it with soil, and then build all your building again? Unfortunately, this is not engineering. So engineers, they came up with I would say, a marvel machine called TBM, tunnel boring machine. Unfortunately, in Canada here, we don't use it because simply we have lots of space. Okay, but in other area of the world where spaces are very tight, so this is the way to go. So I'm gonna share with you here and this video is I think in UK. So let's see the video and see this marvel. And not really my intention is to share with you how this machine works, but it gives you an idea of how those tunnels will be built. So let's see. I'm not going to show you the entire video. I will show you probably half of it until you get the idea of how this machine works, and then we can proceed to how surveying is connected to this kind of work. Let's see.
The average person spends 26 years and 3 months in bed.
When it opens in 2018, Crossrail will connect 28 existing stations to the West End, the City and Canary Wharf through 21 kilometres of new twin-bore tunnels under central London. 8 tunnel boring machines, or TBMs, will drive through the ground to create Crossrail's tunnels. A TBM is 148 meters long and weighs 1,000 tons. This is the equivalent of 14 London buses end to end and a staggering 143 buses in weight. It has a rotating cutter head at the front and a series of trailers behind housing all the mechanical and electrical equipment. There are two types of TBM being used by Crossrail: earth pressure balance TBMs and mix shield TBMs. 6 earth pressure balance machines will be used for the 18 kilometers of tunnel through the clay to the west and the riverbed deposits in the east, while 2 mixed shield machines will be used to drive the tunnels through the chalk beneath the River Thames. Depending on the geology below and the buildings above ground, each TBM will travel between 90 and 150 meters each week, ending up to within a millimeter of where it needs to be. The first part of the TBM's work is the tunneling phase. The earth pressure balance TBM has a cutting wheel which is pressed against the tunnel face by hydraulic cylinders. Inside the cutting wheel, the disc cutters and scraping tool loosen the material. If the earth is unstable and to stop the tunnel face collapsing or digging too fast, the TBM uses the soil that has already been dug out by the cutting wheel to support the tunnel face. This creates a stable environment for the tunneling to move forward. The tunnel face is continuously monitored by pressure sensors. They check the turning power of the cutting wheel and the screw conveyor, and they also keep track of the material that's been excavated. The material is then taken away on conveyor belts. Once the tunneling phase is done, the cutting wheel and screw conveyor are stopped and the ring building phase starts. A complete tunnel ring consists of several lining segments made of pre-built reinforced concrete. These are made in a special factory above ground. They must match the exact size required and are taken into the tunnel on flatbed rail cars. The concrete segments are fed in by the segment feeder and lifted into place using a vacuum. The hydraulic cylinders are temporarily retracted in order to provide enough space for the new segment. The segments are positioned with millimeter precision and held in place by cylinders before being finally bolted into position. The conical keystone is put in from the front to complete the lining ring. Each individual tunnel ring is built in a slightly conical form. This means that curves can be built along the tunnel route by changing the direction of the cone. The hydraulic cylinders are extended again to secure the segment into position. During all this work, the people and machines are protected by the shield skin from the saturated ground where water is under pressure.
So as I said, I think that's enough for you to understand how this machine works. And as I said, this machine is amazing. I've been myself to one of those machines back in 1995 when I was undergrad. And at that time, they were building a big network of tunnels in Cairo. And I mean, really, what I want you to show you is how surveying has been affected and adapted to control this machine to navigate underground. Remember, this machine, it is dropped at the station, and then it navigates itself for a few kilometers to go to the next station, completely blind underground. And it has to be within, the tolerance is very small. It has to come out few millimeter away from where it should be. So which means we have a very small tolerance of errors. Now, let me show you surveying in tunnels. And I'm sorry, I have to go one step backwards. So this video here, I'm going to show you the full video, and I will show you the challenge of doing surveying within tunnel. Please watch, and we'll run some discussion after you guys watch the video. So really, I'm gonna start the discussion here by asking you, like this setting here, is it similar to what you've seen or watched or you've done yourself first year? Like total station are mounted on top of a tripod, I guess. I need some confirmation, please. Again, I cannot see you, so I need some interaction. What do you think? This picture is the same that you did before or you watched before?
Seems similar.
So it's similar, so which means you've seen total stem mounted on a bracket hang from the wall. Is that a normal setting for total stem?
For me, no.
Normally it's on ground. Like it's easy easy to set up on a flat ground, but it's difficult to like balance it in the tunnel.
Exactly. So normally totalization will not be on this setup. Normally totalization will be on top of a tripod, and the tripod is on the ground. We cannot do that here. You can see there is a rail, and if you look at the video carefully, the rail, there is mud, there is underground water coming through the tunnel. So it's very difficult to do that in the tunnel itself. So the only way you can do it, you have to have a mounting bracket that hangs your total station to the walls of your tunnel. Now, I'm asking you one question. Do you guys remember where do we level center our total station? So do we level and center total station above random points or above specific points?
Above specific points.
Do you remember what did we call these points?
No, but I know they are a metal, kind of a metal nails set in the ground.
Okay, thank you so much. That's, I think, Lucas.
Yes.
Okay, so as you said exactly, so we level them and center them above specific point, not above random points. Those points, if you cannot remember, we call them traverse point. Does anybody remember this name? Traverse points? Okay, so you guys remember that traverse points. So those are points that we fix on site and we do some measurement, and ultimately we were able to find their coordinates X, Y, Z. Here is the critical question. These points, are they allowed to move, or we have to fix them in a way that they are fixed and unmoved? What do you think?
They're supposed to stay stationary, not move.
Thank you so much. That's correct. So really the traverse point is supposed to stay stationary, not moving, because simply if they move by mistake or by pushing them or whatever, it means the coordinates that I have for them, they are not valid anymore. Now let's try to apply this on tunnel. So you can see, looks like my traverse point is hang from the wall. Now the question is, those walls, what do you think? These points are stationary or they can potentially move? When I say move, I'm not talking about meters, I'm talking about millimeters. Any idea? Any thoughts?
Well, if the tunnels settle, then it might move some millimeters, something.
Yep, exactly. So you can see the machine, it's based on cutting and vibration. So the machine is very, very very strong, and and remember this thing is below the ground about 30 or 40 meter. So there is a water table and things are moving. And what does it mean if things are moving? I have no other option. My control points or traverse points are on the wall, and there is no way for me to stop them from movement. I'm going to share with you what is the problem. So here is the problem. Control points are moving, which means this is unlike what you've done in the first year. In the first year, you fix some points, you fix them well, so then the coordinates stays the same. What happens if it's out of my control? It is moving anyway, and I have nothing to do to stop them from movement. So here is how what you do. You need to run your traverse daily basis. So these points, the control point or the traverse points, we need to survey them every day. Every day you have to run your traverse and get new coordinates. And please don't think about 2 millimeters are little. Some of you will say, you know what? If it moves 1 or 2 millimeter, 3 millimeter, that's okay. I want you to kind of feel what will be the disaster if this machine goes somewhere else. So if you have a 2 millimeter in every control point, moves by 2 millimeter, and then after a few kilometers, which the machine is digging blindly from the top, it's supposed to go to one station. What happens if the machine gets deviated from its design trajectory? Any help? Do you feel the disaster if the machine did not go on the planned trajectory and deviate to somewhere else? I would say it's a disaster and you cannot fix it. Okay, so that's why tunnel surveying is very, very special. We need to get a fresh measurement every day for the traverse point. Okay, and you can imagine the difficulty. There is no favorable condition in terms of light or even in terms of oxygen. So it's very, very serious surveying in tunnels. Now another example for you. I want you to watch the video and then we can chat. Okay, let's do this.
Duruyor. Yani rica bina gelir aşağı, her yerden geliyor burası. Bizim makine kurtarma şansımız yok. Ya git abla git ya. Şunun makinesinin adı. Kameraya çekin şurayı ya. Sen al işte makineden çık istiyorsan ben alıyorum. Bırak şu makineyi yere atar bırak. Biraz yere. Hocam yapıldı.
Okay, so what you've seen in this video is simply a retaining wall failure, as the title says. So retaining wall is something that is very common. I'm not sure if you know some examples on where we do retaining walls. Any help? Where do we need retaining walls? Did you learn any structure? Have you seen any structure where there is a retaining wall to support the soil?
Similar to this, if you were to go downtown, buy a bunch of other buildings, and you had to do a foundation.
Thank you so much. Really, I was about to tell you this example. Like in downtown, I witnessed myself over the last, I would say 5-6 years, there was a few high-rise building, and you know, the city will not allow any of those structures to build without providing enough parking for the user of the building. It's a must, okay? So we need to build a parking area below the building, and to provide enough, probably you have to build maybe 4 or 5 levels of parking below the ground. Okay, now what to do? You know that from your soil mechanics or geotechnical engineering, you know that soil doesn't stay vertical. So what happens here is you need to build a retaining wall. Again, I'm not going to go through the process or how you do it or what are the soil nails or whatever. No, the thing is here, those retaining walls, they are really, really deep into the ground. You can say, for example, between 15 to 20 meter and sometimes even more. Now, the thing is, when we build a retaining wall, we cannot just build it and just watch until something like what you see in the video happens, because this is simply, it's a disaster. You can imagine, for example, those high-rise buildings, they are along the 7th Avenue in downtown, and you can imagine what happens if this thing happens in downtown. I can tell you, it's a disaster. I myself, like, think about it. Back in before the pandemic, when the C train is in operation, if the C train shuts for a few hours, it will be chaos. If the C train shuts for only a couple of hours, I have done like some of them. I have seen some of them. Okay, so I'm asking you, what happens if this retaining wall falls and simply the C train will also collapse? The city will simply be in chaos. So anyway, what happens is to control this process, surveying is the way to go. So what we do is we simply fix some points on the retaining wall, many of them. And then what we do is we survey these points. We survey them today and tomorrow and every day we do the survey, and sometimes we do the survey twice per day, which means we survey these points in the morning and we survey them in the afternoon. And we can simply know if the wall is in motion or about to move just by looking at the coordinates of the same point over time. So if I survey my point today and I have some coordinates, and I survey the same point tomorrow and I get the same coordinates, it means there is no deformation. It means the wall is stationary, it doesn't move. What happens if I am surveying the point every day and I find significant difference between the coordinates over the time? This tells me that the wall is potentially moving, and in this case, you want to do something. You have to do something. And again, what you need to do, probably you will have to add more soil nails to make your wall stable. So you guys have seen the video and you kind of appreciate that the deformation monitoring is something, it's a must, not a choice. Okay, so here is a few pictures from other projects. Same, this one is not really in Calgary. This one is in the Philippines. I was there, I'm crazy. I'm looking at this hole in the ground. I simply took my camera and immediately took some picture of this excavation. Okay, so same idea. We have retaining wall. They are trying to build some barricade, and you probably can see there is a 15-20 meter big hole in the ground. And I'm going to explain for this later on, but our target cannot be just like the prism that we used last year. So if you have done again in-class survey or online, you learn about the prism, huh? You learn about the prism. So the prism, it's something like a glass, which is typically used in normal survey. In this kind of survey, which is deformation monitoring, we don't use those survey like prism. Look at the top right corner. Look at the top right corner of my slide. You see something called paper prism. Paper prism, and those are very suitable for this application. So what we do is we take those paper prism, which looks like a sticker, and we stick them using epoxy on the walls, and we keep them until for 1 year or 2 years, until the excavation is done and until all the foundation is done, and we are at the level, at the ground level. Okay, one more example. I think we have 10 minutes, so probably we can do that as well. So high-rise building, those building that is 30, 40, 50, 80, 120 stories. Do you think we are going to use the same surveying that you learned the first year to build the high-rise building? Now, let's see. Okay, now, this is a very nice building. I'm not sure exactly where on the earth, but it's lovely, huh? It is lovely. Now, when you look at this building, can I ask you which one you give the credit first? Like when you like this building, and I bet sure all of you guys do. Who is the first will get your attention? Is it the surveyor or the structure engineer or the architect? What do you think?
Architect probably will get the credit.
Absolutely. I myself, when I look at this one, amazing. That's the kind of a very nice architectural design. But I can tell you, when you learn, or if you have learned already about structures and about bending and torsion, you will really appreciate how this guy is standing. Okay, and that's also, if you know about construction, you will also appreciate the structure engineer who came up with this skeleton and the core in the middle, concrete core, that makes this work. And you can see, look at my screen, this is kind of a 3D model of the structure, including kind of a space bracing and this red concrete core in the middle. But I'm asking you, do you think this structure can be built without surveying? Like, you guys, those are very accurate measurement. Like, for example, those are steel members are cut to a length, and there is a very small tolerance of this. How can you put these things in space in the exact place as designed? The answer is surveying. Without surveying, although there is a great effort from architect side, great effort from structure, is very challenging, but also surveying has a big challenge and role in building these structures. Okay, I'm gonna show you a video to kind of appreciate what kind of a special equipment that we use in surveying if we were to build a high-rise building. Okay, let's do it. Okay, so I mean, the first part of the video, I know that's kind of a slides and it's going very fast, and I bet you that you are able to read anything. But really, what I want you to focus on this exactly what they are doing right now. So can anybody guess what those guys are doing right now? Like the person on the bottom on the main floor and the person on the higher floor. Any smart guess?
seen
Don't be
how
scared.
far the building kind of deviated as they went up?
Actually, they are not really measuring deformation, because deformation, it is something happen over time, which means if you wanna go with what you propose, it means I need to do this process now. I need to repropose and redo this method, let's say, or this process, let's say, in a week or a month. So there must be time separation where deformation takes place. But if you see the video, everything happens in few seconds, and deformation don't happen over few seconds. So really, I mean, I know that's not easy, and probably you've never seen this before. But the thing is, when you build a high-rise building, column must align vertically. So all the columns must be on top of each other. And you guys, by now in CVT, you will know what happens if my column are shifted every floor. You know what happens? Like if I build one column and the next column on top of it shifted by 1 centimeter, and the next one by 1 centimeter, and the next one by 1 centimeter, you know, what do we call this shift? Does it have a name? Did you learn any name about this shift in CVT? Did you learn anything about eccentricity?
Yeah, we did learn about eccentricity.
So columns in general, columns, unless intended. So sometimes, for example, we have a building in downtown where the columns are not aligned, but this is on purpose, and the engineer knows that, and it's in purpose, and he considers all the eccentricity, and all the columns are strong enough to take the eccentricity. Remember, eccentricity is not good because it causes bending moment on the column. If the column is exactly on the column below, then there is a centric force. If the column on the top is shifted, then we have a moment, additional moment, due to eccentricity, okay? So here is the point. What those guys are doing are simply copying control points from the main floor, copying to this level. So you look at the lines on my screen. So the person is simply drawing two lines, and the intersection of the two lines, this point is exactly above the point on the main floor. So we are kind of copying, okay, elevating the control point on the main floor to, let's say, a story number 20 or 30. And that's why if you work every time from the same control point, then your columns will align. Your columns will align. So anyway, there is 2 minutes left, and I think there is still one last example. Probably we can cover next class about very specialized kind of surveying called hydrographic surveying, where the surveying is happening below the surface of the water for so many applications. We'll do the next class, but for now, do you guys have any question about what we discussed in class today? So looks like no question, and again, our time is over, and I will see you guys on Thursday. Thank you so much, and enjoy the rest of your day.
Thanks. Have a good day.
Thank you.
Thanks.